it comes to another important topic that is associated with this chapter is nothing but the Arrhenius equation. As we all are aware of the fact that when temperature is changed, there will be obviously some variation in the rate of the reaction. What I mean to say, it has been observed like whenever the temperature is raised by 10 degree, it's experimentally proved that when temperature is raised by 10 degree, it has been observed that the rate of the reaction approximately increases by 2 to 3 folds. So here I have taken a rate. Remember, my dear students, rate constant is nothing but the rate of the reaction. I have taken at a particular temperature, say T degrees Celsius, and when I increase the temperature to or by 10 degree, it has been observed that the rate is increased by 2 to 3 folds. This is the experimental observation. And this ratio of the two rate constants which are differing by 10 degree is usually referred as temperature coefficient. So let's ascertain why there is such an increase or phenomenal increase in the rate of the reaction when temperature is increased. As we are well aware of the fact that the frequent collisions between the reactant molecules is responsible for a reaction to take place. What I mean to say, when you take the reactants, when they are undergoing a chemical reaction, there are rapid collisions that are taking place because of which this reaction is taking place. And initially, it has been assumed that rate of the reaction is directly proportional to the number of collisions. So this was a preliminary assumption that rate of the reaction is directly proportional to the number of collisions that are taking place per unit time, which happens to be the wrong assumption, because if you take a molecule of P2 particle size, it has been observed that it's colliding with Cl2 to yield methyl chloride, and this reaction happens to be indeed very fast, as there are approximately 10 to the power 26 collisions taking place in 1 second. So this relationship or this fact would suggest this postulate. But when it comes to the same methane, when getting oxidized by the vanadium pentoxide to give formic acid, the number of collisions are approximately the same as the previous one, but it has been observed that this reaction is taking not less than 72 hours for the completion. That means it's a very slow reaction. So therefore, let's not say that rate is just directly proportional to the number of collisions. Rather, we will say that rate of a chemical reaction is dependent on the collisions, not the total, only the collisions which are yielding the product. So you can make out one point very clearly, that these collisions are not elastic collisions. Here the momentum is not conserved. There is some variation in the momentum. So you can see here that rate is not totally depending upon the number of collisions, rather it is depending upon the collisions which are yielding rise to the product, which are referred as the effective or fruitful collisions, which are also referred as the properly oriented collisions. So this term would better explain the occurrence of these fruitful collisions. So what I mean to say that if you take X number of particles, reactant particles that are actively involved in the collisions, we are not depending upon the total number of collisions, rather we are depending upon the fruitful collisions. So let me ascertain what exactly this fruitful collision means. For that, I would like to take a simple example where, say, you have chloroform which is supposed to be chlorinated for the next time, wherein I can anticipate the formation of CCl4. So here you see this chlorine radical is supposed to collide with the chloroform molecule, and in this case the probability of chlorine radical attacking at this CH bond which it is supposed to replace is only 25%. So can you see here that out of the total 4 bonds what we have, the probability of attack by the chlorine radical is only 25%, that is 1/4. So therefore it's mere useless or meaningless to say that this is depending upon the total number of collisions, rather it is depending upon only the fruitful collisions. Like this can be extended to the molecular orbital theory which we commonly study in chemical bonding. You know, my dear students, that there are 2 types of the interferences, wave interferences. One you call as constructive, the other is called as destructive. As we all know that when there is symmetry retained between the orbitals, it would yield the bonding molecular orbital. So I am taking this as the analogical to the concept that we are discussing here. So there is an analogy, you can see here clearly that from the molecular orbital theory I have taken the constructive interference which is taking place between the reactant molecules. But as you say, when the same is overlapping or interfering with the other wave of the opposite symmetry, we would say that these two are heading away, creating a node. So this can be mapped to the concept that we are studying here. So if they are properly oriented, results in the fruitful collisions, otherwise not. So therefore, let's understand the fact that when there are fruitful collisions, the potential energy of the system consistently increases. Remember, my dear students, these are not elastic collisions. Here, when these two are undergoing the fruitful collisions, the energy of the system has consistently increased. That is, reactant molecules are colliding with each other to raise their energy to the maximum, which is commonly referred as the activated complex, and then they are forming the product. So if I take potential energy on the y-axis and reaction coordinate, which happens to be the distance between the molecules on the x-axis, I can see here the collision that are taking place between the two. So here the collision between the reactant particles which are fruitful are taking them to the energy barrier, and whichever are crossing this energy barrier are yielding the product. So here we say that it requires minimum this much amount of energy for the reactant molecules to give rise to the product. So what I mean to say that there is some minimum amount of energy required for the reactant to form product, which you can find at the energy barrier, known as the cutoff energy or threshold energy. So remember, this is not possessed, this is acquired. This is acquired by virtue of what? The fruitful collisions. So during the fruitful collision, the energy of the system is rises to the highest level and then drops down. So here the reactant molecule that are crossing this barrier are able to form the product, and whichever are not are lying down here itself. So what we have to do here, when we are rising the temperature, we are providing them the extra energy in the form of kinetic energy. As we all are aware of the fact from kinetic molecular theory of gases, the average kinetic energy of the gas molecule or average translational kinetic energy of the gas molecule is a function of, that is linear function of the temperature. Hence, when temperature is increased, we are making these molecules to acquire certain amount of energy to reach this point. It is something like the students who are failing to crack these exams are acquiring the admission into the top engineering colleges by paying the management fees. So this is exactly like the same. Like we are making these particles, we are giving it extra amount from outside so that these reactant molecules are crossing the energy barrier because there is a direct connection. So from kinetic gas theory itself, you see, when I take the number of molecules, these are Maxwell distribution curves, versus the velocity or kinetic energy that I take on the x-axis, you will find that at a particular temperature T1, say this is the graph, and when temperature is increased to T2, the graph will be little diffused. Here we know that T2 is greater than T1. So here you can see area under this particular cross section, which would give you the number of reactant molecules that are crossing the energy barrier is increased when you are increasing the temperature. So here we are taking the help of what you call this Maxwell distribution curves to explain the variation of the kinetic energy of the reactant molecules with the temperature, and thus we are supporting the fact that when temperature is increased, more and more molecules are crossing the E barrier because we are providing the extra amount of energy. We are not making them participate in the fruitful collisions, but rather we are increasing their probability to collide faster, and thus maybe the fruitful collisions are increasing, giving rise to the product. So here, after seeing this, we will understand that there is certainly some amount of activation which is being done to these reactant molecules that are miserably failing to undergo the fruitful collisions, and that amount of energy which we are giving here, referred generally as EA, is nothing but the activation energy. You know, every system inherently possesses some amount of energy, either it could be the reactant or the product, which we commonly refer as the average energy, which happens to be usually the internal energy associated with the particles. So here there is some average energy, and there is some activation energy, and there is some threshold energy, as we have discussed earlier, and we can derive a relationship between these three energies by saying that the activation energy, that is the amount of energy required to excite the molecules to cross the energy barrier. The management fees is nothing but equivalent to the threshold energy and the average energy difference. So if you can provide this much through the temperature variation, we can successfully make more and more molecules to cross the E barrier. So here one point to be noted is that the lesser the value of this activation energy, higher will be the rate, or it is easy that this reaction could take place. So simply speaking, when we are carrying out a chemical reaction, we are ensuring that this gap is little lesser. So here EA, I'll write it as EF as well, because I am going to talk about the activation energy related to the backward reaction. Here, if I take the activation energy of the backward reaction, this is EB, this is EF. You can see here whichever side the activation energy is less, whichever side the activation energy is low, that side is going to take place little easily. So you can see here EF is less than EB, so forward is very feasible compared to the backward. So here the difference between EF and EB yield us something. What? If I take the potential energy as the replica of the heats, I can say that the difference between EF and EB will turn out to be the delta H of the reaction. So you know there are two types of reaction, one you call as exothermic, the other is endothermic. I mean to say delta H, if is less than 0, heat released, obviously EF value is less than EB. This particular case we can see on the board. Whereas in the other case where delta H value happens to be greater than 0, the EF value is greater than EB. So these two relationships, which are very frequently asked in JEE, by giving the delta H value, the activation energy of one particular side, it could be forward or backward, we can get the activation energy of the other side, or we can predict whether the reaction is exothermic or endothermic depending upon the values of these two. So now the question would really arise, what's really happening when a catalyst is being added to the reaction mixture? See my dear students, if you are following a particular path, wherein the activation energy say is EA, this is in the absence of catalyst. There is no catalyst that is at present there in the reaction vessel. So when you are adding a catalyst, it could be the negative catalyst or positive catalyst. Negative catalyst or poison. The positive catalyst which we talk about, we say that catalyst lowers the activation energy. Remember my dear student that this activation energy is a constant value, but this catalyst is going to provide an alternate path where the activation energy is lesser than anticipated. Suppose if this is EC, EC is less than EA. So this catalyst is going to provide another path, another mechanism, another route where the activation energy happens to be little lower. It is not depleting the activation energy of a particular reaction, rather it is suggesting you to follow another path, another mechanism wherein the activation energy is less. When it comes to the poison, it will suggest you the path wherein the activation energy will be more. So for example, you want to carry out the controlled oxidation, controlled reduction, etc. In that case, we will be adding a poison. The purpose of this poison is to slower the rate. So in most of the cases, we will be poisoning in order to slow the rate of the reaction by providing alternate path wherein the activation energy happens to be higher. So here you can see that how this activation energy varies when the catalyst is added. When it comes to any equation that is related to this particular theory, you will see here that the rate is directly dependent on the temperature by this exponential relationship. So the derivation part is completely out of our syllabus. So we are focusing on the applications of this equation, which is commonly referred as Arrhenius equation. So here, as I told you, rate constant is nothing but the rate of the reaction. So here, whatever I am encircling happen to be the variables, that is, with the temperature, the rate of the reaction would vary, rate or rate constant, one and the same, and there is an exponential relationship. And here absolute temperature you need to take, that is temperature in degree Kelvin. You know, R is universal gas constant, whose values we borrow from the gaseous state, and the values of this R should be according to the value of EA given. For example, if your activation energy is given in calories, you take R in calories, that is 1.978. If this is given in joules, you take this in joules, 8.314. So accordingly you have to vary the values of R. So here this EA is nothing but the activation energy, and when it comes to this A, it is nothing but the frequency factor. We know everything in this equation except this frequency factor, and before that let me tell you that these two are going to remain constant throughout. At the smaller temperature ranges, we say that these two are constant. At the higher temperature range, these EA value even might change, but we are not concerned about that. We are concerned only about the smaller temperature ranges, where we take these two values to be constant. So here we define this Arrhenius factor or frequency factor as the total number of collisions taking place per unit volume per unit time. So this speaks about the total number of collisions that are taking place. Now you see, we have this K, which talks about the fruitful collisions, and this 8 talks about the total number of collisions. So therefore the ratio of these two will give you what? The fraction of the collisions. These are total number of collisions, and this is the fruitful collision. So this will give you the fraction of collisions that are crossing the E barrier or yielding the product, which is commonly referred as Boltzmann factor, which will give you the fraction of reacted molecules giving the product. So most of the times the questions are asked about this Boltzmann factor also. So you can see here, if I am plotting a graph here between K and T, there is an exponential variation. If you see here that this shows the decrease, right? So in one of such questions which are being asked in JEE, the graph between K and T is asked. It has been studied that the value of K increases with temperature, so this is option A which is given. Happens to be incorrect because this shows the variation of temperature decreases the value of K. Remember, my dear students, that there is obviously an increase in the value of this K when temperature is increased, and we can obtain the slope by virtue of the differentiation of this one. dk by dt will give you the slope. So here the slope will help you to find the value of this Boltzmann factor sometimes. So here this equation, whatever you have taken, is applicable to all reactions except zero order, because in zero order reaction there is no significance to the number of collisions that are taking place between the reactant molecules. Despite the nuclear decay follow first order kinetics, this is not applicable to the nuclear decay process. because in nuclear decay also this has got no significance at all. What I mean to say is that this unstable nuclide doesn't require to collide with the another unstable nuclide to participate in the nuclear reaction. So therefore, despite it's a first order reaction, this is not applicable for the nuclear decay. So remember that this is neither applicable to the zero order reaction nor to the what you call the nuclear decay reactions. So now moving on further, if you take the equation and see the graph related facts, now let us take up a call asked by the student. Yeah, please go ahead.
Hello.
Hello. Yeah, I can hear you, my dear student. Please go ahead.
Hello.
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 Yeah, I can hear you. Please carry on. Go ahead with your doubt.
So if you add a catalyst, activation energy decreases, no sir?
Yeah.
Hello.
Yeah, please go ahead.
If it decreases, activation energy is inversely proportional to the rate. Then rate constant is also dependent on rate and activation energy, no sir? Then how can it be a constant?
Yeah, if your doubt is over, let me explain this particular thing related to the role of the catalyst in this equation. So I could hear your doubt, and now let me answer your query. Now you see that
I can hear you, sir.
Please look at whatever I am writing on the board. Probably this will explain little better.
Okay.
Yeah, please look at here. This is the equation what we have for the variation of the rate with the temperature. As asked by you, if there is the variation of EA, there will be the variation of K, then how can it be the constant? Remember, my dear student, that here this path, whatever you have taken, has the activation energy, say E1. I hope you are following me. This path, when I have not added any catalyst, this path has the activation energy E1. So this equation is valid when the activation energy is E1. This is in the absence of catalyst. There is no catalyst that is present. Now when I am adding a catalyst, when I am taking another reaction into account, you can see here that I am following an alternate path wherein the activation energy is different. Say I'll call it as E2. So obviously, as I said, E2 value is less than E1. Therefore, I am not manipulating this equation, I am not changing it. What I am just doing is, I am writing another equation wherein the activation energy has decreased to E2. So here if I say that the rate constant of the reaction is K1, listen, please try to understand, this is not or no longer remained as the same reaction. This has changed. For a given reaction, obviously the K varies with temperature. But since the reaction itself has changed, we have changed the path itself, it will become K2. We haven't changed the temperature. Without the influence of this temperature, we have changed the activation energy. Doesn't mean that we are writing different activation energies for the same reaction. Actually, we are writing the different activation energies for the different reactions, because every path, every mechanism here considered as one reaction. As this Arrhenius equation is valid for each path. Now the activation energy, whatever I have written, is not the activation energy of the previous reaction. Previous reaction activation energy is going to be same, but now this is a different reaction altogether when I have added the catalyst. So it will totally change. So maybe you are thinking that K is influenced only by temperature, but here this K is totally different because I am writing this K for a different path. So I hope your doubt is rectified or cleared. So moving on further, the equation part, whatever we have, can be put up in a graphical manner. For example, at temperature T1, say the rate constant is K1 and temperature T2 has changed its rate constant to T2 without changing the other things. Now when I write it simply, I'll write K2 divided by K1 is equal to E power EA. If I take this EA as common, I'll write it as 1 by T1 minus 1 by T2. So here when I am applying the logarithm, this is what we call as the integrated form or the extended form of the Arrhenius equation. Now there are few important things related to this equation. If I write it, there are two important things to be discussed. Those things are, see, at the first instance, now I hope you got it. I have taken at temperature T1 the rate constant to be K1 and at temperature T2 it has changed to K2. I have taken the ratio. The ratio is turning out to be this much. I applied the logarithm on both the sides to get this final integrated form. Now after getting this, now let me take two instances. The questions can be made interesting about this concept. The first one is, I'll take two first order reactions. A giving rise to products and B giving rise to product. The activation energy of the first one is E1 and second one is E2. It's given that the activation energy of the first one is greater than that of second one. If both the reactions are subjected to the same change of temperature, suppose the temperature of the reactions, both the reactions which happen to be the first order, have been changed from T1 to T2, which reaction will have more influence of this variation of temperature? My question is, if you have two different reactions with different activation energies and both the reactions are subjected to same change of temperature, the question is which reaction will have more influence of changing the temperature. I am not asking you which reaction is faster, as we all know that this is faster, but where the influence or rise of temperature will be higher. Just see here, this term is constant for both the reactions, so your K2 by K1, this shows the influence on the rates, solely dependent. In fact, this is also constant, is dependent on what? The activation energy, or we can say that K2 by K1 in this case is directly proportional to the activation energy. So whichever reaction has a higher activation energy is going to have more impact of rising the temperature. So this point we have to understand. So increase of temperature shows more impact on the reaction with more activation energy. This is one such important point to be noted. Moving on to the second point associated with this is that if I take one reaction with a consistent activation energy. Suppose this reaction is studied at two instances. One is when the temperature is raised from 25 to 35 degrees Celsius. The other is the temperature is raised in the 525 to 535 degrees range. So now the question would really arise, at what situation there will be more impact of rise in temperature. Now you can see in the same equation, just observe the constant values, what are all remaining constant. You see here in this case T2 minus T1, the variation of temperature is only by 10 degree. So what I mean to say that this whole thing remained constant. So this for K2 by K1 we can say is in this case inversely proportional to the product of the temperatures. So you can see if the temperatures are higher, the impact will be less. So that is why we will always say that when you carry out a particular reaction, you will see the phenomenal growth. For example, you boil water, the extent of boiling initially would be higher compared to the later stages. As you are growing the temperature, the impact of variation of temperature won't be higher. So we will say that increase of temperature is more effective at lower temperature ranges. So these are certain important factors that are associated with the chemical kinetics. And after that, when the questions are asked from Arrhenius equation, they are simple and straightforward. Just what you need to do is you have to substitute the data, but sometimes they might give you the delta H as well as the activation energy of the forward reaction to find the activation energy of the backward, and thus you will be finding out the rate constant of the backward reaction as well. Moving on further, if there are questions which are asked related to this particular chapter, for example, let me give you a simple question which is asked previously in JEE. So now these questions may be even related to the radioactivity, as we all know that all nuclear decay follow first order kinetics. So it could be either related to the nuclear reactions or chemical reaction. The type of questions that are being asked are pretty simple. For example, you see when I deal with certain questions that are asked in chemical and nuclear reactions separately, here it's given that there are two separate first order reactions that are taking place, say A giving rise to products and B giving rise to products. It has been given that the half-life period of this reaction is some 5 minutes and this is 15 minutes. And it's also given that the initial concentration of this A is 4 times the initial concentration of B. Then the question is, at what time the concentration of A becomes equal to the concentration of B. See, when such type of questions are asked, instead of relying on the equations, if you depend upon the concepts, it will be pretty simple for you. What I mean to say here, if I assume that the concentration of P initially as X, it's given that the initial concentration of A is 4x, and as per the given half-life, after 15 minutes this will become x by 2, and here because the half-life period is 5 minutes, after 5 minutes this has become 2x, another 5 minutes it will become x, and 5 minutes more it is becoming x by 2. That the concentration of A and B are turning out to be equal at 15 minutes span. You can see here clearly. So otherwise what we do is we will take that lengthy equation and we will say AT equal to A naught e power minus KT and BT equal to B naught e power minus K2 into T, and we will substitute that half-lives and we will equate this AT with BT and solve it in a little complex manner. But if you depend upon the concepts, it will be pretty simpler for you. For example, there is a, let me take another question which is asked in nuclear chemistry. As we know, for a first order decay, if initial nuclides given are N naught, after your first half-life it will become N naught by 2. After another half-life it will become N naught by 4 and so on, because every time the half-life period is independent of the initial number of nuclide in case of the first order reaction, because you have seen yesterday we have derived the half is a constant value. So it's a constant, it keeps on halving when you take each half-life period. So the question is that suppose if I start with N naught number of nuclides, if the question is number of nuclides decayed during 11th day, what you will do? Suppose the half-life period is given as some 10 hours. In all such cases, what you have to do is we know one thing very clearly, that number of nuclei that are remaining after t seconds is equal to N naught into 1 by 2 whole power n, where n is the number of half-lives. You can see here, first half-life it is N naught into 1 by 2, second half-life it is N naught into 1 by 2 whole square, that is N naught by 4, third half-life it will be N naught into 1 by 2 whole cube. So I'll be using rather this formula, which is pretty simple when it comes to the nuclear chemistry reactions. So what I'll do is, when I have to find out the number of nuclides decayed during 11th day, I'll find out the number of nuclides remained after 10 days, happens to be N naught into 1 by 2 number of half-lives. If I say for 10 hours it is 1 half-life, indeed after 10 hours it will turn out to be 1 half-life only. And I'll also find out the number of nuclides remaining after 11 days, which is equal to N naught into 1 by 2 whole power 11 by 10, because for every 10 hours there is 1 half-life, for every 11 hours how many half-lives. So here the number of nuclides remained after 10 days is N10 and number of nuclides remained after 11 days is N11. So number of nuclides decayed during 11th day is nothing but N10 minus N11, which you need to find out. So wherein you will be given the N naught. In the JEE question, this N naught is given as 0.1 mole or 0.1 into Avogadro number of nuclides. So this is how you are going to solve the questions which are very simple.